Air flows into a constant area, well insulated, circular duct with a Mach number of 0.6, static pressure of 10 psi, which means pounds per square inch absolute, and static pressure of 500 rankings. The duct has a diameter of 1 foot and a coefficient of friction of 0.004. If the duct is 8 feet long, determine the Mach number, static pressure, static temperature, and total pressure ratio. Show on a TS diagram. Okay, so I'd like to start with a figure. So let's do that. I don't like this. So I'm gonna make a nice figure. I'm assuming I'm looking at it from the side so that this is not, so that this is looks like a rectangle, but it's round. And so they're telling me that the diameter of this thing, that the diameter D, this length right here, oops, let me make this a little bit better. That this diameter, they're telling me right here, that this diameter is, well, it's the whole thing. I hope you that's not very clear. So we want to do the whole length. And we're saying that this diameter is what? Well, they told us it's 1.0 feet. Okay. And the duct has a diameter of 1.0 feet and a CF of 0.004. This is 8 feet long. So this is 8 feet. What is this? This is going to be, we call it L1. Okay? And determine the Mach number, static pressure, static temperature. Well, they give us a Mach number at the beginning. So we have a Mach 1, and we have a static temperature, T1, and a static pressure, P1, right here. The duct is 8 feet long. Determine the Mach number. So we want to know the Mach number here, the static pressure, and the static temperature. So T2, P2. Now, we're starting subsonic. There's going to be friction. I'll do it in a different color. I'll do it in red because I see it as a loss of something. So friction. That's going to constrain the flow. Obviously, this is exaggerated. But we're not going to reach supersonic here. However, if we imagine to extend this further, and since it's imaginary, I'm going to dot it because it's not actually there. What we're going to get is eventually this is, we're assuming it just keeps on getting smaller and smaller. And here we're going to get Mach equals 1. And we call this second part, this imaginary length, L2 star. It's the length that you need to increase it by to get a Mach of 1. We are talking about a Fanno flow. Why is it a Fanno flow? Well, because they gave us a coefficient of friction, and friction is related to Fanno flow if we assume it's adiabatic. So that brings me to the assumptions. What can we assume? Well, we can assume 1D flow, right? Because we're representing with a single number for each property, we're representing this whole region, each cross section. So we can say it's a 1D flow. And then what else? 1D flow, we're going to assume single in, single out. We're going to assume steady flow. And we're also going to assume CPG. And what else? And we're going to assume it's adiabatic, because otherwise we'd have to combine Rally and Fanno flow. So this is adiabatic. Adiabatic. So once we do all of that, how are we going to actually solve this problem? So let's write the solve portion of this, and let's see. Well, you know a relationship from the supplemental data pack. So let's go over to the supplemental data pack, and let me see. Supplemental data pack. So if you go down below the oblique shock chart here, you have the Fanno flow parameters. Remember, Fanno goes with friction. And indeed, you have this first term over here, for which we do know D. We don't know L, but we know the Mach number. So we could find this whole term, because this whole term is a function of the Mach number. So what we do is we're going to go to 0.6 here, and we're going to look at this number from here. And from here, since we know D and we know CF, we can find L star. So 0.6, that's going to give us 0.4908. So we're going to go back to where we were, and we can say that with M1, supplemental data pack, we're going to get that CF4 times L star over D is equal to, and I already forgot, 0.4908. So 0.4908. So now that we have this, well, we have our D. We just need to figure out what L is. And L should be this one right here, if I got my nomenclature right, which I think I should review just to make sure that I'm not tricking anyone. So let's see, how did I do it in my notes? In my notes, L star is the whole thing, and L2 star is the other thing. So I think I would want to find this whole thing would be L star, the whole length. So just keep that in mind. What we can do is we can find L star. L star is going to be equal to 4CF times L star over D times D over 4CF. And what we get out of that, sorry, dropped it again. What we get out of that is what? 0.4908. That's non-dimensional, it doesn't have any units, multiplied by the diameter, which is 1 foot, divided by 4 times the coefficient of friction, which is 0.004 times 0.004. And it's a coefficient, so it does not have units. And now we want to divide it by, that's it. So we're going to get a length in feet. That makes sense, right? So let's get a calculator out, and let's see what this number turns out to be. So we have 0.4908. 0.4908 divided by 0.016, 0.00, and we get 30.675. So 30.675 feet is our L star. Now, to find L2, that's going to be equal to L star minus L1. And that's going to be equal to, did they give us, that was 8, right? L star minus L1, so that's going to be 30.675 feet minus 8 feet. So we're going to get 22.675 feet. Now, why is that useful? Well, now what we do is we find 4 CFL2 star over D. And I have to make sure I'm doing this right. So let's check together that I'm doing this correctly. So we're going to go to lesson 38. And they said that, so we found this. We solved for L1 star, which is this one right here, the big L. Then we find L2, which leads to, that's where we are right now, which leads to M2. So let's go back to the homework here. And we want to find this. Well, that's going to be what? It's going to be 4 times 0.004 times 22.675 feet divided by 1 foot. So the feet cancel out here and here. And then we input everything into the calculator and look at what the output is going to be, what the result is going to be. So 4 times, I want a fraction, 4 times 0.004 times 22.675 divided by 1. So we really don't need a denominator. So that's going to be 0.3628. 0.3628. Now, from supplemental data pack, we can say that M2 is going to be equal to, well, let's find where that is 3628. So this goes down. We're expecting the flow, if it's subsonic, to go faster, right? Because we're compressing it and it started subsonic. So let's see. We want this to go down, and we see it's going down here. Where's my pen? We're going down, and this is going down, which makes sense because our ratio went down to 0.3628, which is between these two, so we can say 0.635. And our flow sped up because we constrained it and it was super subsonic. So let me go back here. It's going to be 0.635. And that's going to be our M2. Now the next thing I'm going to show you is how to find the P2 and the T2. I'll see you there.